Okay, ladies and gentlemen, you don't have space for these notes. You don't need to take them. It's just an intro to what does being exponential even mean? What does exponential growth mean? So something that we're familiar with is multiplication. Multiplication is repeated addition. What does that mean? Well, if you had 3n, you'd have 3 times n. So you'd have the number 3 n times. This would essentially be 3 plus 3 plus 3 plus 3 all the way until you had n threes. Does that make sense? So if you had 6 threes, you'd have 3 6 times, which would be 18. Multiplication is repeated addition. In the world of exponents, exponents represent something different. They represent repeated multiplication. So if you had the same kind of number, if you started with 3, here we multiplied it by n, meaning we had n threes added together. Here it's noted as an exponent, 3 to the power of n. And what this means is that you have 3 times 3 times 3 times 3, on, and n represents the number of factors. Which one do you think grows more rapidly? Multiplication, okay? So if we were to graph these things, just again, quick reference. If you were to graph 3n, well, if you had 0 n's, you'd be at 0. If you had 1 n, you'd be at 3. If you were at 2 n's, and maybe I can just change my scale a little bit, 1 n, 3, 2, 6. If you had 3, you'd have 9, right? 3 times 3, and you'd end up with a line going up constant. Every time you went over 1, you'd go up 3, over 1, up 3, over 1, up 3. In the world of exponents, if you have something to the power of 0, anything to the power of 0 is 1. So it already is starting above 0. And then you're multiplying it by 3. So if you have one of them, you have 3, which goes through the same point. But then if you have 2 of them, you have 3 times 3, which is 9, which would already be up here. And then you would have 3 times 3 times 3, which would be 27. Then you have 3 times 3 times 3 times 3, which would be 81. And you can keep going on that way, and it grows really quickly. So the graph of an exponent looks like that. So the exponential graph will grow much more rapidly than a linear graph if the number is greater than 1. Okay?
Exponent grows more rapidly.
So this whole unit is about exponential functions and skills working with exponential expressions. Okay? We start just kind of observing some growth patterns among bacteria and other things like that. So in your notebook, lesson 3.1, example 1 says model exponential growth. It says a type of bacteria grows so that it triples in number every day. So whatever you have on one day, the next day you have triple that, then triple that, then triple that, then triple that, exponential growth. On the day that Roger begins observing the bacteria, a sample has a population of 100. We are going to find the population after each of the first 4 days, and we're going to do it 2 different ways. So here we go. In step 1, the first table that you have there on the left, you have day and population. Okay, we're going to start at day 0. So day 0 is the first day that Roger looks, and how many bacteria are there? What's the population? 100. Okay. On day 1, so 1 day after he starts, a full 24-hour period, that 100 gets multiplied by 3 and becomes 300.
Okay, try to get the whole equation.
Yes, please, because we're going to make some connections to the next table as well. On the second day, he looks, and that 300 that he originally had triples again, and now there are, on day 3, where there were 900, the 900 has tripled again, and he now has 2,700. Go ahead and fill in the rest of the chart. I think there's only 2 more lines left. 1 more line left. Okay, looking at this chart, we can clearly see the process. The process is repeated multiplication. It says, take the value that you are given, multiply it by 3. Then take that and multiply by 3 again. Then take that, multiply by 3 again. Then take that, multiply by 3 again.
Why do you multiply by 3?
Because it's tripling.
It says it in the description.
Yeah, it's tripling. If it were doubling, we'd multiply by 2. If it were quadrupling, we'd multiply by 4. If it was tenfold, we'd multiply by 10. Now, to better illustrate the relationship between each day and the actual population, we actually don't use this strategy. We write it a different way. What does that mean? In order to actually say, okay, well, you know, how, Roger, how much bacteria, what population do you expect on the 7th day? Well, you'd have to keep on doing this all the way down until you got to day 7. That's not that efficient. That doesn't directly relate the day to the number of bacteria. It's kind of a pain in the butt, the process. So we can use exponents, and we can write things in terms of the original population. So again, how many did he start with on day 0? There were 100. Okay? Now instead of saying what happened on each subsequent day, we're just going to say how many times did it triple. So on the first day, you had 100, but it is going to triple 1 time. You have 1 factor of 3. Okay, 3 to the power of 1 is just 3, so this is still just 300. We know that. The answers are all right here already. But now we're not going to bring that 300 down and multiply it by 3. Instead, we're going to take our original population again, and on the second day, it will have tripled twice. 3 to the power of 2, which just means 100 times 3 times 3, right? Tripled twice. Well, what's that? 3 squared is 9. 9 times 100 is 900. What are we going to write for day 3?
3 to the power of 3.
So you start with 100, and you multiply it by 3 factors of 3. 3 times 3 times 3, or 3 to the power of 3. 3 to the power of 3 is 27. Multiply it by 100, 2700. Next line, try to write on your own. On the 4th day, we will have tripled 4 times. So you have 4 factors of 3 times 100, 8100. So now you can see the relationship, and you have a little box there at the very bottom. Now we have a function relating the population to the day. Okay, if we do this, if we put a little p here to represent population, we put a little n here to represent the number, which day it is. Well, now we know that p with respect to n is going to be your initial amount, 100, times 3 to the power of n. So it's times 3 as many days as there are. It's going to triple every day. So if you're looking for the 8th day, the number of bacteria on the 8th day, you just have to sub in n equals 8. You do 3 to the power of 8 times it by 100. And this is the population on that day. You couldn't do that on this side. Okay, on this side, you'd have to keep on taking a number and multiplying by 3 and getting the next number and multiplying by 3 and getting the next number and multiplying by 3 and on and on and on. Well, what if you want to watch this thing grow for a month and you want to be able to compare the number on different days? You want to have a function that gets you there a little more easily.
Would you ask us to create a function?
Okay, the next one asks us to graph this function. In order to graph it, we're just going to plot its points. So you have a grid on your book. If you go 2 boxes in and draw a vertical line, and then from the bottom you go 2 boxes up and you draw a horizontal line, okay, you'll have a nice little grid. The values of n, that is our independent variable. So that's easy. Day 1, day 2, day 3, day 4, day 5. Good enough. And then going up vertically, you're going to look at the values that you have as far as the population, right? We're going to have population with respect to n is going to be your vertical axes here. the dependent variable, and the highest we get is 8100. So I'd probably just write 10,000 somewhere at the top and then start splitting it. Yours will obviously be more accurate.
I don't think so. Wow, what's our highest number here?
And then all we're going to do is plot our points in order to graph it, and you'll see what the graph eventually starts to look like. So on day 0, he has 100. It's way down here. On day 1, there are 300. That's still way down here. On day 2, there are 900. That's there-ish. On day 4, there are 8,100. Oh, sorry, day 3, I skipped. Day 3 has 2,700. Oh, we're doing something here. And day 4, 8,100. Somewhere up here. Okay, yours will be much more beautiful, obviously. The information there is plotted. Is it or is it not a function?
Sorry?
2 questions, I guess. Number 1, why am I not, in this case, connecting these dots with a smooth curve? Why am I just leaving them as dots? So in this experiment, he has a designated time each day that he's going to check. He's only going to check once a day. There is no information provided or relevant for half days or in between this. So it's just the key points that are here and not a curve in between. The only values that we're thinking about is day 1, day 2, day 3, day 4. You can't ask for day 2.5. It wasn't part of the experiment. Is it a function?
Yeah, because it passes the line test.
So you could think of it that way. Hypothetically, if we did a smooth curve, it would pass the vertical line test. And even as is, it does pass the vertical line test because no vertical line will go through 2 points. Basically, there's a distinct output for each input. When you put in 1, you will get 300. When you put in 3, you will get 2,700. You will not put in 3 and get 900 or put in 3 and get 8,100, okay? There's one output for each input. So one element, each element in the domain corresponds to exactly one element in the range. We can make a note. This is a function because each element in the domain corresponds to exactly one element in the range. There's no mystery of what you're going to get out if you know what you're putting in. So in your workbook, we look at B. Assuming this trend continues, predict the population after 1 week. So 7 days. What do we need to do to determine the population after 7 days?
Plug in 7.
Yeah, we're looking for P of 7. So we just plug in 7 where we see an N. You might be able to break out your calculator for this one. And the one next door says after 2 weeks, which would be 14 days. Days is N, so I'm looking for the population after 14 days, means I sub in 14 for N, and I click away on my calculator. What did you get?
I'm not sure how this thing works.
Okay, just to show it in multiple steps, we're taking our original 100, it's getting multiplied by 3 7 times. 3 to the power of 7 is 2187. So our final answer is 2187 with 2 zeros at the end, which is 218,700. So after 1 week, the population of bacteria will be 218,700. After 2 weeks, don't be tricked on when you're doing this. It doesn't just double, okay? It's not, the population doubles from 7 to 14, so then this number has to double. No, it's a new relationship. It's now exponent. You have double the factors of 3. You're multiplying it by 3 twice as many times. It's tripling twice as many times. So what is that? That's 100. 3 to the power of 14 is 4,782,969. I would never write this in my practice problems. I would go straight down to the next step. Copying this and re-putting it in your calculator is just way too much room for error. Or you could write it down and then just leave it in your calculator. Don't type it again. Your calculator will save that answer. All you have to do is hit times 100 and you're good to go. What does it end up being?
The same number with 2 zeros at the end.
Yeah. 478,296,900. So after 2 weeks, there's our population of bacteria if the same trend continues. Roger doesn't necessarily do the experiment for 2 weeks, but after the first 5 days, he has a pretty good pattern. Now, how did he predict that? Well, we're going to find out what how to kind of predict what your exponent is or what your ratio is, what the repeated factor is going to be. That's in the next section of this example. So describe the pattern of finite differences for this relationship. We can go ahead and put our population numbers back in. We already know what those are. 100, 300, 900, 2700, and 8100. And then you have another column called the first differences. Do you remember how to get first differences?
I think so. Can you refresh my memory?
Okay, so you simply, it's y2 minus y1. y2 minus y1. So we take 300 minus 100, so you're working up and you're subtracting. So that's 200. Then you take 900 minus 300, which is 600. 2700 minus 900, 1800. 8100 minus 2700 is 5400, 5400. Now, if we were doing a linear relation, all these numbers would be constant. What are you noticing?
They're not.
They're not. They're not constant, so it's certainly not linear. What do you think about second differences? Are the second differences going to be constant?
No.
Okay, let's try our second differences. Second differences mean you're going to take the first differences and perform the same operation. y2 minus y1. So 600 minus 200. Then you have 1800 minus 600. Then you have 5400 minus 1800. Constant or no?
No.
Okay. Again, if the first differences were constant, we would know it's linear. It's not, so they're not. Second differences. If second differences were constant, what would that mean? What type of function has constant second differences? Quadratic. It's not. We already knew that. It's called exponential. The point is, what is... No, it's exponential. The point is to find the relationship between these numbers. Don't give up. Don't turn off your brain. You have to think through this. You're right. These are not constant and these are not constant. But what is the relationship between 5400 and 1800?
They're divisible by 2.
Close. They are divisible by 2. Yeah. How do you get from 200 to 600? How do you get from 600 to 1800? 18 to 54? 4 to 12? 12 to 36? Okay, so what happened? The ratio between each difference, the ratio between each value, the ratio between successive first differences and successive second differences and actually population are all the ratio is the same. They're divisible by 3, or they're how do I say this? 600 over 200 is the exact same as 1800 over 600. Is the same as 54 over 18. Is the same as 12 over 4. Is the same as 36 over 12. Is the same as 27 over 9. Is the same as 81 over 27. Okay, so the ratio of successive first differences, we're going to write this down at the bottom. The ratio of successive first differences is the same.
I'm in.
Okay, the ratio of successive first differences is the same, as is the ratio of successive second differences. Okay, later on, you're going to have to be able to check this. So I'm going to give you just a couple, just exactly what we're talking about here. The ratio of successive first differences, that means 600 over 200. That created a ratio, and it is a ratio of successive first differences because they come right after each other. Okay, I couldn't go 1800 over 200. That would mess up the ratio. 1800 and 200 are not successive. They're not right beside each other. So I have to take 600 and 200. And then my next option would be, by the way, that equals 3. Then I would have to take 1800 over 600. I always have to work the same direction, okay? And that's 3. And 5400 over 1800, that's also 3. Okay? That's what we mean by the ratio, which is one number over another number, of successive, means right in a row, of the first differences are equal, are the same. And again, the same exact thing happened when we moved over to the second differences. We had 1200 over 400, which is 3, and we had 3600 over 1200, which is 3. Okay? Same ratio, constant ratio. Okay, at the top of the next page, you have a little bit of space for some notes. The notes are on exponential growth. Exponential growth. What are some applications of this? This happens in science all the time when you're talking about like bacteria growth or population growth. It happens in economics and finances if you're investing money and you're earning a certain percentage on those things. Yeah, so it happens in science and business all the time, and we're going to talk about it now. This is a pattern of growth in which each term is multiplied by a constant amount. So repeated multiplication. It's a pattern of growth in which each term is multiplied by a constant amount. You want to know how to get the next term? You just multiply it by the same thing you multiplied the previous one by. And the key for growth is that in brackets you can write this is greater than 1. That means the thing that you multiply it by, the repeated factor, has to be greater than 1. What happens if the repeated factor is 1? You're just multiplying it by 1, which doesn't change anything. What about if the repeated factor is less than 1? If I keep on multiplying it by, 0.75, it'll get smaller and smaller and smaller. Okay, so growth is only the case where the repeated multiplier is greater than 1. Okay? Right. Good. It produces a graph that is constantly increasing. The graph is constantly increasing.
Okay.
At an increasing rate. That's really the key. The graph is increasing at an increasing rate. So if we drew a little sketch of it, if you have some space off to the side, okay, don't draw my first picture. My first picture is linear. This is a graph that is constantly increasing, okay? But it is not increasing at an increasing rate. It's increasing at a constant rate. It's called its slope. It's not what we're dealing with here. What we're dealing with here is a graph that increases but the rate of increase is also constantly increasing. So it's growing, but it's growing faster and 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 faster, and that never changes. Okay? Now, as it's growing up, it's also still constantly moving this way. Okay? And actually my graph is incomplete because it goes both ways. But what's interesting is it will never hit 0.
Is that exponential?
This is an exponential graph, okay? This is what they will look like when we're dealing with exponential growth. Hold on, guys. Quick question came up. Why will it never go all the way down to 0? We can figure that out by looking at one. So let's just think about positive x land for a second. Let's say you had 2 to the power of 3, then 2 to the power of 2, then 2 to the power of 1, then 2 to the power of 0, then 2 to the power of -1, 2 to the power of -2. And let's say that's good enough to prove my point. And we're going to just look at what each one of those equals and what's happening. So do you know what 2 to the power of 3 is?
Oh, because it's
2 to the power of 3 is 8. 2 to the power of 2 has one less factor of 2. So I just need to take that number and divide it in half. I need to divide it by 2 because it has one less factor of 2. So 2 squared is 2 times 2 is 4. 2 to the power of 1 is one factor of 2. That's just 2. Look what's happening. Cut in half, cut in half. 2 to the power of 0, guess what? Cut in half. Okay? 2 to the power of -1, well, we learned about this. 2 to the power of -1 is the same as 1 over 2. Okay, you just bump your base into the denominator, and it's 2 to the power of 1 in the denominator. Well, guess what half of 1 is? Okay, what about 2 to the power of -2? I could take half of this. Half of half is 1/4. And look at that. In the denominator is 2 to the power of 2. Okay?
So it will never touch 0.
So it will never touch 0. It will only keep getting smaller and smaller. So if I did 2 to the power of -3, look, 2 to the power of 3 is 8. But now I have 1 over 2 to the power of 3. It's getting smaller and smaller and smaller and smaller, and actually it's cutting the distance between the curve and the x-axis in half every time, which is a lot. But it will still never ever get there. It will only cut it in half, which means half of the space remains. Every time. Yes? Good. This probably confuses you right now. We'll tackle that at a different point. Okay, example 2. Apply a 0 exponent in a model. So this is kind of exactly what we just talked about a little bit in a little bit more detail. We're going to take the data from the table and we're going to demonstrate the meaning of 3 to the power of 0. So really this is exactly what we just did. So you have your days, 4, 3, 2, 1, 0. Backwards now. And the population that we had 8,100. Don't write that. We're going to write what we actually had. We wrote 100 times 3 to the power of 4 equals 8,100. Next row, you have 100 times 3 to the power of 3, which is 2,700. So we're looking at the same data. Now we're just looking at it backwards in order to demonstrate what happens when you have a power of 0. 3 to the power of 2 is 900. On day 1, we have one factor of 3, which is 300. And on the very first day that Roger, the initial day, the population is 100. But look at your exponents. 4, 3, 2, 1, 0. Okay? Again, that's just kind of another way of showing it. It doesn't really explain it.
Yeah, you're still multiplying it by 3, so technically. Looking at it backwards, we're dividing by 3 to get to a previous day, or multiplying by 1/3 to get to a previous day. But at any rate, all this is saying is that 3 to the power of 0 must be 1 because we know we started with 100. So 3 to the power of 0 must be 1 because 1 times 100 is 100. Yes? You can also graph it and then you could find that out. What does that mean? It means that in a standard exponential function, okay, it will always go through 0, 1. If you didn't move it up or down, okay, it will always go through 0, 1. How can I write that again? When x equals 0, when the exponent is 0, y equals 1. Okay, in this case, it's been multiplied by 100. So in this case, it actually goes through 0, 100. Okay, in this one that's right here is 0, 100. But if you just have y equals 2 to the power of x, this thing will go through the point 0, 1. And if you had y to the power of 10 to the power, sorry, y equals 10 to the power of x, that also goes through 0, 1. And if you had y equals 5 to the power of x, that also goes through 0, 1. Because anything raised to the power of 0 is 1 based on this same idea. Okay? I can demonstrate it using the laws of exponents. Do you know anything about the laws of exponents? Like when you have a base to the power of something times the same base to a different exponent, you just add the exponents.
Yeah.
Okay. When you have, okay, that's good. So now, when you have a base, we'll do the exact same situation, but this time you're over another exponent. Do you know how to get, and maybe I'll change my answers a little bit. I'll do 3 and 2. Do you know how to, the rule for this is basically there's 3 factors of 2 here and 2 factors here. What you end up getting is 2 to the power of 3 minus 2. Does that make sense? 2 to the power of 3 minus 2, which is 2 to the power of 1. Now, what happens if we're in a situation where we have 2 to the power of 4 and 2 to the power of 4? But you get 2 to the power of 4 minus 4. What's 4 minus 4? 2 to the power of 0. But this is the same quantity over the same quantity, which is always 1. Okay?
Now that makes sense.
Good. You can take all that great new knowledge that you have and apply it to your practice problems, which you'll find on page 155. Numbers 1 through 10.
That's
Not
a
like
lot
the
of
last
questions.
part.